In this next lesson, we're going to talk about what's known as the shell method. Alright, so as an example, let's suppose we want to find the volume of a solid of revolution that's generated by rotating the area bounded by the x-axis and y equals x minus x squared about the y-axis. Alright, so let's take a look at our region, and let's see here. So this function y equals x minus x squared, that's going to be a polynomial that is opening downward. If I factor out an x, it reveals to me that I have zeros of 0 and 1 itself. So I could just put 0 and 1 in here. I'm not really sure how high this would reach, but I'll just draw in a general polynomial here, or general parabola, with those two zeros. Okay, that's great. Now, it's bounded by the x-axis, so that's y equals 0. And so now we can clearly see the region that we are encompassing, and I'm, of course, meant to shade that in. There we go. Okay, so with that, let's take a look at the axis we're rotating around. It says here to rotate around the y-axis, so if I'm rotating around the y-axis, here's the thing. In order to use a disk method, I would need to be perpendicular to the axis of rotation. But the thing is, in order to do that, I would have to have the ability to know what the left and right endpoints of this rectangle are. All right, which means I would need to take my function y equals x minus x squared and solve it in terms of y. So I need to get x by itself. Well, I could factor out an x, and there may be some additional algebra that I could do to kind of get x by itself, but in general, that's not really going to be all that easy to do. So it would be nice if I could just leave it as a function that it is, just leave it in terms of x, and enable myself to simply use a vertical rectangle. Because if I could use a vertical rectangle, which would be parallel to the axis of rotation, then I wouldn't have to solve this function for a different variable. I could just leave it as y equals x minus x squared. So that would be really nice. But what happens if I rotate this around the y-axis? Well, here's what it might look like, and I'm not going to be able to do great at illustrating this, but I'll do the best I can. Hopefully you can imagine it along with me. So here is my region, okay, and I'm rotating that region around the y-axis. So it's going to basically map on the other side here as well, and it's going to create this kind of like a donut shape for us. Okay, so this would kind of be like the top of the donut where that top part rotates around. All the bottom parts would also rotate around here and create this kind of a region, if you can imagine what I'm drawing there. I wish I could do a better job of that. But really, the most important thing that you understand here is that if I take a single rectangle and rotate this rectangle around the y-axis. Okay, so that point would rotate around like that. This point would rotate basically alongside it. And then the bottom would also rotate around, and this would rotate around as well. And it makes this shape that is kind of like a shell. All right, so this region creates a hollow shell kind of region. And hopefully you can imagine what I'm drawing here, since I'm not doing a great job at actually drawing it. All right. This hollow shell that's created, it has a thickness. Okay, so the thickness of this thing, its width that is, we can just call, say, like delta x. All right, because it's based off of the width of these rectangles, and we always let those rectangles go to 0. Okay, so that's the width of this rectangle. The height of the rectangle is defined by the height of the function. It's whatever the function happens to be, f of x, or it could be g of y, doesn't matter. But the height of the shell is defined by the height of the function, which is just given by the value of the function. And the approximation really comes down to this one last little bit. So you're really going to have to do some imagining here. If I take this rotated region and I, like cut it in half, all right? So if I just like make a cut line, right along here or something, just grab some scissors and cut along, and just lay it down flat. All right, then that region would look like this. If I was able to do this. All right, so it would be a rectangular solid. The height of this rectangular solid is still defined by the height of the shell itself, so it's defined by the function. The width of this rectangular solid is still going to be delta x, which will go to 0. And the other dimension here of this rectangular solid is going to be from here over to here, and that is the length. And the length of this is going to be, so if you look back over here at our picture, the length is based off of a circle, okay? And a circle wraps around by its circumference, okay? So the distance this point travels all the way around would be the circumference of this circle, which is dependent upon how far away from the x-axis you are, okay? So you have this, this distance here of your rectangle from the x-axis. That's just whatever x is. So whatever this x value is for the base of the rectangle, that's your distance from the x-axis. And you can think of that as a radius. And if you think of that as a radius, well, you could take that and multiply it by 2 pi and come up with the circumference of that circle, which is the length of this rectangle. All right, so the volume of this rectangle then would be, I know we generally say length times width times height, but I'm going to say here length times height times width. And the reason I'm ordering it that way is because the length is this factor 2 pi times x. The height is the function f of x, and the width is delta x. So very often what we end up with is the volume of one of these shells is 2 pi x times our function times delta x. Now, if we were to add up a bunch of different approximations, we could take an integral and then come up with the actual volume of the region. All right, so that's what I have in the next part of the example. So the volume of one shell is 2 pi x times your function times delta x. And if you integrate across the entire interval, we have the volume of this region, this rotated region that is, 0 to 1. And it's 0 to 1 because we started here with x equals 0 and it ends at x equals 1. So the rectangle here goes between those values of 2 pi times x, and that makes the circumference of those shells, times x minus x squared, because that's the height of the shell at any particular point x, times dx. Now, if I put this into fn int, I could leave the factor 2 pi on the outside of this integral, and so essentially what I would need to put into the integral would be the endpoints, 0 and 1, of course, and this would be x times the quantity x minus x squared. Or certainly I could have just distributed the x into these parentheses. It doesn't really make a whole lot of difference. But that gives me this, which works out to 1/12. Remember, I took the 2 pi out, so I have 2 pi times 1/12. 2 goes into 12 6 times, so that gives me a total volume of pi over 6. Now, there's one little bit of things or a couple of things I want to wrap up here before I go on to another example. So, sometimes if you have an axis that you're rotating around that's something other than the x-axis or the y-axis, this factor that makes up the circumference is going to have to be adjusted. So if the axis is some other vertical or horizontal line, it can just easily be adjusted as effectively 2 pi times 2 minus x or y plus 4 or whatever. And we'll see some examples that do that. But for the most part, if you're rotating around the x or the y-axis, this factor that represents the length of your rectangle or your shell is always going to be just 2 pi x or 2 pi y, depending on which axis you're rotating around. All right, so just kind of get used to that and try not to forget it. What I like to do is think of these formulas not as like, rote things to process and memorize, but I like to think of them in terms of, what's similar to something else that I already know. So like, for instance, the disk method. I had already mentioned that the disk method, when you set that up, it's the integral from a to b of pi times some function r squared dx. So essentially an area of a circle. Okay. When we look at the shell method and think about how we can identify something that we already know, then we could say here, of course, our volume is integral from a to b of 2 pi x, or that might get changed depending, but for now, just 2 pi x or y. And then the function, and finally, dx or dy. All right, so this is, of course, a length of the shell if that is stretched out the way we did. This is a height of the shell, and this represents a width. So length times height times width means we have the volume of a rectangular prism. All right, and if you just think of it, if you take out the dx, length times height, you're multiplying two things together, you're getting the area of a rectangle versus the area of a circle. And that should help you kind of get set up in these problems. I tend to just actually start with, this is the volume from A to B of length, let me try again there. Length times height times width and go from there. And just fill in what these are. Define R as the region bounded above by the graph of f of x equals x squared and below by the x-axis over the interval 1 to 2. Find the volume of the solid of revolution formed by revolving R around the y-axis. Okay, let's take a look at what this region looks like. All right, so I think everything should be in the first quadrant. And my x interval is 1 to 2, so I'll just 1, 2 there. And since it's square, let me make this a little bit smaller. 1, 2, 3, 4. Okay, so let's take a look here. All right, f of x equals x squared. That would have 0, 0, 1, 1, 2, 4 as part of it. Okay. Below by the x-axis. All right. And on the interval from 1 to 2, and those are on the x. Okay, so we can clearly see the bounded region here. All right, and here's what I want to do. I want to rotate that around the y-axis. All right, now, whenever you approach a problem, you have a choice. You can choose to either use shell method, or you can choose to use a disk or washer method. It's all going to, what you end up doing in the end is all dependent upon how you orient your rectangle. If you orient parallel to the axis of rotation, you're going to use the shell. If it's perpendicular to the axis of rotation, it would be a disk method. What I generally do is I set up a vertical rectangle regardless of, if that makes me do the shell or the disk method. Just because the functions written as functions of x are just easier for me to, think about. So I go with a vertical rectangle, and then if I have any reason that I can't use a vertical rectangle, I'll switch. All right, so let's go with this and see what happens. Now, this would be parallel to my axis of rotation. So when I'm parallel to the axis of rotation, then that means I would be using the shell method. So this shell method, I get my volume from integrating from A to B. This, well, let me write it out like this. So I'll say I need the length of each shell times the height of each shell, and then technically the width, but that's always going to either be dy or dx, just depending on the orientation of your rectangle. So I'm just going to go ahead and put that in as dx. All right, now the height of each shell. So when I rotate this rectangle around the y-axis, the height of each shell is just the function itself. So that's pretty straightforward. So this is going to be, I'll fill that out in a second. So the height is just x squared. All right, the length of each shell. Oh, sorry. The length of each shell is the circumference of the shell formed when you rotate this rectangle around the y-axis. And so just to show you again here, when I rotate this rectangle around this axis, it's a distance of x away from the y-axis. So whatever x is, that's the distance away it is. And that is a radius. So that's the radius of this shell. And then the length of the shell is the circumference, which is 2 pi times that radius, which is just x. So it almost always ends up being just 2 pi x or 2 pi y, especially if you're rotating around the x or y axes. Now, when we are rotating, we're going between the x values 1 and 2. And that's great. We're pretty much all set up here. We would have, I'm going to factor out the 2 pi, simplify the inside a little bit, and just call it x cubed dx. And to be honest, I could use fn_int, or I probably could skip it on this one. It's pretty straightforward power rule integral here. But just so I don't make an arithmetic error. All right, so this is x cubed dx. And change that into a fraction. We get 15 fourths, so this would be 2 pi times 15 fourths. And that leaves me with 15 pi over 2. Okay, so there we are. We've got it solved. We've figured out the volume of this region. Now, question is, could we have done this a different way? And the answer is yeah, and a lot of times you really can. Let's try it with the disk washer methods and see what's different. So let me just copy down my region again real quickly. All right, so that point there, that point there, there. Okay, so here's my region now. Same region that's getting rotated. Rotating around the same axis. It's just, I'm going to be using horizontal rectangles instead. And the important thing is that these are perpendicular to the axis of rotation, so that means we would use the disk or the washer method. And I tend to really just say disk because it's not much different. The washer is just a generalization, that's all. Now, there's one little issue here. There's actually 2 subregions when I do it this way. Because the thing is, the most positive part of this rectangle and the most negative part of this rectangle is not the same function on the entire interval from y equals 0 up to up here, which is y equals 4. Because I would be integrating from 0 to 4. The thing is, the most positive part of the rectangle is the same on the entire interval, but it's not on the bottom. Okay, so setting up our volume then would require 2 integrals, one going from 0 up to y equals 1, so y equals 0 to y equals 1. And to get the volume of this region rotated around the y-axis, I would need to use the washer method, and here's what I would need to do. Let me put pi on the outside here. The outer radius is this side, which is always 2, so that's going to be 2 squared. And then we're going to subtract the inner radius, which would always be 1 squared, and that would be dy. Okay, so then that would give me the volume of this part. Now I would need to add to that the volume of the rotated region from 1 up to 4 of the rest of this. So here the outer radius for the washer method would be 2, and then of course that gets squared from the formula. The inner radius would always be this function right here. The function is y equals x squared, which becomes x equals the square root of y. All right, so then it's going to be the square root of y squared dy. And you should be able to plug this into your FN int at this point and get the same answer. We should still get 15 pi over 2. I'm not going to go through that, but I just really want to illustrate to you that very often you can use two different methods to come up with an answer. But in general, there's one that works a lot easier than the other. So you want to try and start developing methods of choosing the easiest one. So for instance, my method is start with a vertical rectangle, because usually if you have vertical rectangles, the functions are a bit easier to think about. Okay, but if the vertical rectangle leads to needing to do multiple regions, or you have to rewrite a function in terms of another variable that's not easily done, then I would go with horizontal rectangles at that point. And that's generally how I choose most of the time. So just be thinking about that as you go through some of your homework, although it's not really till the review sheet that you'll see a lot of mixed problems. A lot of the ones in the homework really kind of have to be done one way or the other. So, all right.